Hi everybody. Uh, Thank you for being here. My name is Cohen. I'm going to talk about a recently published study that we did here in IDC in collaboration with Bar-Ilan University and the Weizmann Institute of Science. Um, I'm going to talk about high-performance BCIs using missing hand representation in long-term amputees. And the study was published recently in the Neural Engineering Conference in Shanghai. Okay, so when we first wanted to do the study, we didn't really know what we are going to see and in the brain of amputees. We wanted to allow a group of amputees to control a virtual avatar using their missing hand and intact hands, and of course their legs, for the purpose of controlling a virtual avatar in a virtual environment. We wanted to do it in a single trial scenario and do it in real time. In the picture, what we see here is a scene from the movie Avatar, which is kind of similar to what we're doing. There's a device which looks like an fMRI machine, and there's a guy who goes into it and controls an external body or an external presentation of his body. And ultimately, that's the goal of BCI research. We had a couple of research questions going into the study. We wanted to know if amputees can actually control the missing arm and use it to control BCI, use it to control an external device such as an avatar. We wanted to know if their performance can be compared to a group of healthy, or should I say control subject who have both of their arms. And we wanted to understand what goes on in their brain following a trauma or following a BCI experiment. And what we see here is one of our subjects in which I think we placed EMG sensors on his shoulder, which the purpose of placing the EMG sensor was just to see if there is no movement in the shoulder when he performs the BCI task. And in the BCI world, usually you see studies that talk about motor imagery. We chose to do motor movement with in our experiment, and usually motor imagery is typically associated with a healthy subject or paralyzed subject, and they want to prove that the motor imagery is something that you can do with in a typical BCI experiment scenario. But actually, this is not needed with amputees because they weren't born paralyzed. You don't need to teach them how to move their hands. They actually, they know how to move their fingers. They just don't have the hand to do it at the moment. And this is one of the interesting things about amputees. We wanted to see if there's actually brain activation in the motor areas and which kind of brain activation, and can they use it to control some kind of a device. And if we talk about BCI as a world of where we are positioned in the world of BCI, in BCI you have invasive and non-invasive techniques, and we are in the non-invasive technique, which is using fMRI. And there's a bunch of ways to do BCI. You can do neurofeedback. You can do some kind of communication and control. Sometimes you see it with locked-in patients. And we are somewhere on the side. We try to operate robots and navigate avatars and control, in general, control some kind of external device. Our group of subjects, we had 3 amputees. Each one of them reported mild to high phantom pains. And we had a control group of people with both limbs, and all of our subjects were right-handed. Um, um, our experiment was conducted using an fMRI machine, which is actually an MRI machine that records functional data. We use the whole brain. We scan the whole brain, which is a high-resolution scan, and we get high-resolution scan every 2 seconds in an experiment. And if we have, you can imagine 12 or 20 minutes of experiment, every 2 seconds we get about 200,000 features that we can use to see what goes on inside the brain during the experiment. The signal that we are using when we talk about fMRI recordings is called the Bolt signal, and it's actually an indirect measurement of neural activity, which means that if you give a subject an auditory cue or some kind of cue, you get the peak of the signals about 8 seconds after the cue occurred. And you typically associate fMRI with sort of a slow control of an external device, which means that if I want to classify what happened 8 seconds ago, the subject is already doing his next command. So, so unlike EEG, when the data flows in milliseconds transmitted, the Bolt signals limits us to intervals of up to 8 seconds of actions. So what is the data that we're using when we talk about fMRI? We actually get a 3D brain scan, as you can see here. We have 32 brain slices, and each one of them is a slice, a vertical slice of the brain. And the whole square, if we look at the whole square, which is actually a 3D cube, we have 204,000 voxels, and those voxels, we use them as features for our training algorithm. And in each 12-minute experiment, we only have 40 samples. This is a mistake. And if we, and in a complete experiment in which we have about 4 to 5 training sessions, we have only 160 samples. So in the world of machine learning, we have too many features and not enough samples. And what we want to do is to converge automatically on all the relevant RIs, regions of interest in the brain. We don't want to use the noise, the black areas. We don't want to use the eyes. We just want to use the relevant brain areas that correlate with the task at hand. Okay, so when we get the data, there's a few steps that we need to follow in order to converge on those areas. First of all, we need to assign a label for each sample based on the protocol. So imagine a subject getting a command, an auditory command to move his hand. That sample is associated with, let's say the command is move your left hand, that sample is associated with a left hand label. So we are actually trying to solve a classification problem in the world of machine learning. As I've mentioned, we remove the noise, which is all the black area around the brain. We want to remove the eyes because we don't want the eyes to give us some sort of bias regarding what the subject did. Sometimes the subject is looking at the direction of the movement, so we don't want the fMRI to be a really expensive eye tracker. We just want to use the brain itself. And the next step is actually, in order to converge on the relevant areas, we use a feature selection algorithm, which is called information gain, which helps us select only the relevant voxels inside the brain that are relevant for the problem itself. Following that, we normalize the data and fit it into a training algorithm. But before we do that, this is how the dimensionality reduction or the feature selection is seen on top of a 3D brain. And we see all the colored areas. These are the voxels from the entire brain that we converge on. So this is the right-hand representation, the left-hand representation, and over here we see the legs, the activated voxels that belong to the leg our eye, region of interest. Okay, so as I mentioned, we are trying to solve a classification problem. We have a few experimental sessions. We train our data we train our algorithm on data that comes 6 seconds after a cue. So if you imagine this sort of signal that peaks around 8 seconds after a cue, we take the signal itself 6 seconds before, 6 seconds after a cue, in order to train a multi-class SVM, which is, I'm sure everybody knows, it's a support vector machine classifier. We use 4 classes, which are actions for left, right, forward, and null. And null is actually a command for the don't do anything. We use a linear kernel, which is probably, it worked the best, which it's probably because the motor areas for the task are probably linearly separable in several geographic regions in anatomical areas in the brain itself. So it's probably easy for the algorithm to separate them. Which 2 minutes? Shit. Okay. Sorry. Okay. So please censor me. So if we want to we want to see how well our subjects perform. Here we see in the blue the classification accuracy 6 seconds after a cue for the amputees and the control group. And this is based on the simple protocol. And we can see that the accuracy is above 90%, and the statistical deviation is very small, and there is actually no statistical significance between the accuracies. And inside, if we want to compare the accuracy, the amount of the accuracy between the missing hand and the intact hand for the amputee groups, we can see that there's almost no difference 8 seconds after a cue. There's some variability here between the intact hand and the missing hand, but the accuracy levels are pretty high. Here we can see that there, in a BCI task, there's no difference between percentage usage of amputated versus intact hand for the group of amputees. It's almost the same, about 20% out of the total task. Okay, so the whole thing was to train a classifier. But as soon as we have the classifier, we want to give the subject some kind of a BCI task. And we call this a future task. And the subject needs to go as fast as possible and collects all the disks. And we want to measure the performance and see what happens in the brain. And here we can quickly see that the groups, both groups, amputees and control, have nearly the same amount of performance. The amputees are obviously, there are some mistakes in the path, in the virtual path. This is an overhead view of the path you've seen a slide before. And the most important thing, is what happens in the brain, at least visually and analytically, if you want to compare the control group and the amputees. And we can see that for the control group, there's some kind of symmetry between the activation, almost some kind of symmetry. Some subjects have a little bit less than on the left hemisphere than on the right hemisphere, depending on their on their specificity. And for the group of amputees, you can see there's some plasticity going on, and there's an expansion of activated voxels across other regions, which are not existing in the control group. And obviously, there is enough activation to control a BCI with similar performance measures to the control group. Okay, I guess that's it. But I can show some a movie if I have the time. I don't know. Do I have the time? Where's the guy in charge? No time. Ah, here you are. Okay. Let's make a vote out of it. No? Okay. Okay. So I don't have any footage from the amputee experiment, but I have this one, which is a subject from our lab actually is controlling a human robot using two brain systems, the visual and the motor systems in the brain. And the task is to do some kind of navigation task around the chair. And as soon as the robot, which is controlled by the subject, teleoperated by the subject, is seeing, you see, the sign says, face, okay. So the subject needs to look at the table and concentrate on one of the items, and we want the system to converge and to decide for us what the subject is attentive to, which is either the house, the tool, or the face itself. And if the classification is correct, then the robot hand is will point towards one of the categories. This experiment is using the system that I described earlier for this purpose. I guess we can finish here. Thank you very much, everybody.